In this video we are going to talk about 10 ways the universe could end. So before starting this video, like this video and subscribe to our YouTube channel for future updates. Today, as we look out into the universe, it's simple to be completely in awe of everything we can find. Our night sky contains only a small portion of the Milky Way stars, a few thousand out of hundreds of billions. The Milky Way is but one of the trillions of galaxies that make up the observable universe, which spans a distance of roughly 46 billion light-years in all directions. And it all started with the Big Bang, a hot, dense, fast-expanding state, 13.8 billion years ago. As soon as we can say that our universe is composed of both matter and radiation, we may move on to explain how the cosmos evolved into its current form using the known rules of physics. But everything is still changing, expanding, and producing new stars. How will it turn out? What science says is as follows. Astronomers employ two distinct methods to quantify the expansion of space at various points and distances in the past: standard candles, L, and standard rulers, R. We can deduce the history of the universe's expansion based on the way that various parameters, such as luminosity or angular size, change with distance. The distance ladder's candle approach results in a speed of 73 km per second per mpc. The early signal approach yields 67 km per second per mpc using the ruler. For a very long time, researchers who investigated the composition and development of the universe debated between three scenarios, each of which was supported by the expanding universe and the straightforward physics of general relativity. On the one hand, gravity acts as an attractive force that draws everything together. It is controlled by the matter and energy, in all of their manifestations, that are present in the universe. The initial expansion rate, on the other hand, works to tear everything apart. The greatest race in history between gravity and expansion rate got underway with the Big Bang. Which will prevail in our universe in the end? According to traditional logic, the solution to that issue should decide the future of the universe. Here are the possibilities that we considered. In a big crunch, the universe collapses once more. The rapid beginning of the expansion and the abundance of materials and radiation helped to bring everything back together. If there is too much matter and energy, the universe will expand to a certain point before contracting back to its original size and collapsing. A big freeze results from the infinite expansion of the universe. The same as before, everything begins, but this time there isn't enough matter and energy to stop the expansion. As the rate of expansion keeps declining but never reaches zero, the universe will continue to grow eternally. The expansion of the universe stops and becomes zero. Imagine the ambiguous circumstance that lies in between the two examples above. We would collapse if there were one more proton; if there were one fewer, we would expand indefinitely. The universe expands eternally under this crucial, or Goldilocks, scenario, albeit at the slowest conceivable rate. We only needed to measure how quickly the universe was growing and how that expansion rate varied over time to determine whether theory was accurate. The rest would be determined by physics. Due to the universe's growing volume, matter and radiation lose density as it expands, while dark energy is a type of energy that exists in space itself. The dark energy density is constant throughout the universe's expansion as new space is produced. One of the main goals of contemporary astrophysics was it. You can determine how much the fabric of space is changing now by measuring the rate at which the universe was expanding. You can determine prior changes to the structure of space by observing how the expansion rate has varied throughout time. When you combine those two pieces of knowledge, you can determine what the universe is made of and in what proportions by looking at how the expansion rate has evolved through time. According to our best knowledge and based on these findings, the universe is composed of around 0.01% radiation, 0.1% neutrinos, 4.9% normal matter, 27% dark matter, and 68% dark energy. For some, this quest dates back to the 1920s, but it received an unexpected response in the late 1990s. In the past, the expanding universe evolved from a smaller, hotter, denser, more uniform state that is now full of galaxies and complex structure. Beyond the known matter and radiation, there must be some new type of energy driving the current period of accelerated expansion. What does it mean for our future if dark energy predominates the expansion of the universe? Everything relies on how dark energy changes over time, if at all. These are the 5 options. Number 5. Dark energy is a cosmic constant that dominates expansion. Given the greatest facts we have at this time, this is the default choice. Dark energy is a non-zero amount of energy that is innate to the structure of space itself, whereas matter is a non-zero amount of energy that dilutes as the universe expands and becomes less dense. The dark energy density doesn't change as the universe enlarges, hence the expansion rate asymptotes at a positive number rather than 0. This causes the universe to grow enormously and finally push everything outside of our little community away. Under these circumstances, 97% of the observable universe is already inaccessible. Number 4. Dark energy is dynamic and progressively gets stronger. Dark energy suggests that space maintains a constant energy density since it seems to be a brand new type of energy that is built into space itself. But it's also possible that it's evolving. It might be weakening in magnitude, which would hasten the expansion of the universe over time. This is one way it might be evolving. It would appear as though farther away items were moving away from us faster and faster. Even worse, if dark energy grew stronger, all currently gravitationally bound objects, including galaxy clusters, individual galaxies, the solar system, and even atoms, would eventually become unbound. Subatomic particles and the fabric of space itself would be torn apart in the closing moments of the universe. Another possible outcome is the fate of Big Rip. Even though the energy densities of matter, radiation, and dark energy are well understood, the equation of state for dark energy still has a lot of space for error. It might be steady, but it also might get stronger or weaker with time. Number 3. Dark energy decays with time because it is dynamic. What other way could dark energy evolve? It may weaken instead of strengthening. Yes, the expansion rate is consistent with the energy density of space remaining constant, but this energy density may also be decreasing. The Big Freeze is one of the initial possibilities that could result from it decaying to 0, as was stated above. The expansion of the universe would continue, but it wouldn't collapse due to a lack of matter and other sources of energy. But if it deteriorates and turns negative, it might result in a big crunch, which is one of the other options. The energy inherent to space that permeates the entire universe has the potential to suddenly change directions and collapse space. The time frame for these changes is confined to being far longer than the period of time since the Big Bang, but it is still possible that they will happen. The various directions in which dark energy might change in the future. The universe might be able to regenerate if it stays the same or grows stronger, into a big rip, whereas turning the other way could result in a big crunch. Number 2. Dark energy might change into another type of energy, reviving the cosmos. Another possibility emerges if dark energy doesn't diminish but instead stays the same or perhaps grows stronger. The energy that currently makes up the fabric of space might not last in its current form forever. Instead, it might undergo a transformation into matter and radiation, much like what happened when cosmic inflation came to an end and the hot Big Bang got going. Dark energy will produce a very, very cold and diffuse Big Bang, where only neutrinos and photons can self-create, if it continues to be constant until that time. However, if dark energy gains power, it might cause an inflation-like condition followed by a brand new, extremely energetic Big Bang. This is the simplest technique to revive the universe and establish cyclical-like conditions that give the newly formed universe a second chance to act similarly to ours. The simplest explanation for inflation is that it began at the summit of a metaphorical hill, where it continued, and then rolled into a valley, where it came to an end and gave rise to the hot Big Bang. It would be feasible to quantum tunnel into a lower energy state if that valley isn't at 0 but rather at any positive, non-zero value, which would have negative repercussions for the universe as we know it today. Number 1. Dark energy will decay, wiping out the known universe, and is related to the zero-point energy of the quantum vacuum. The most damaging scenario is this one. What if dark energy isn't the real value of empty space in the lowest energy configuration but rather the outcome of symmetries breaking into a false minimum configuration early in the universe? If so, it would be possible for it to quantum tunnel into a state with lower energy, altering the laws of physics and eradicating all of the bound states, i.e., particles, that exist in quantum fields at the moment. If this particular aspect of the quantum vacuum is unstable, then wherever this decay takes place, it will lead to the annihilation of the entire universe in a bubble that spreads outward at the speed of light. We would also be instantly destroyed if such a signal were to ever come to us. Comparing the Hubble's viewing area, top left, to what WFIRST will be able to see in the same length of time and at the same depth. We will be able to observe more far-off supernovae than ever thanks to FIRST's wide-field perspective, which will help scientists better understand and constrain the properties of dark energy. Although we are unsure of which of these scenarios best describes our universe, the data strongly supports the first hypothesis, which postulates that dark energy is a real constant. The amount of flexibility for dark energy to vary is now constrained by our observations of how the universe has developed, especially in light of the cosmic microwave background radiation and the large-scale structure of the universe. What do you think about this video? Do let us know in the comments section below. If you enjoyed this video and want to hear from us again, be sure to hit that subscribe button before you go.